Remember that the size of an atom is usually smaller than the wavelength of a given form of energy or of light. And so when an atom is encountered by a form of energy, whether it's visible light or some other type of electromagnetic energy, these forms of electromagnetic or radiant energy that don't require physical contact can supply electrons that are orbiting in the atoms with energy and allow those electrons to move around about that nucleus. Some characteristics of this electromagnetic or radiant energy is that it travels in a wave type fashion, transverse type wave as opposed to a compression type wave. It can travel through empty space. It does not require a medium like air or water, much like sound requires a medium. And it moves very, very rapidly, and pretty much at the speed of light, which is 3.0 times 10 to the 8th meters per second. Now that's in a vacuum, but for all intents and purposes, it pretty much is that same value, even in air, to the number of sig figs that we usually denote. If we take a look at this illustration here, you can see several things. First of all, you can see that the visible area of the spectrum is indeed a very thin slice of the overall electromagnetic spectrum. You can see some of the different types of energies or the different types of waves and their corresponding frequencies as well as wavelengths. The frequencies indicated by the powers of 10 and the wavelengths depicted graphically there by the size of the waves and the distance between the wave peaks. So you see that light that is lower in frequency and has longer wavelengths than visible light are things like your radio waves, microwaves, infrared waves, and these are all considered generally low energy waves. Waves that have higher frequencies than the visible spectrum and consequently shorter wavelengths are going to have higher energy, and these would correspond to things like ultraviolet, X-rays, and gamma rays. And so taking all of these put together, this creates what we refer to collectively as the electromagnetic spectrum. When we think about one of these waves, there's two main properties that we consider. The first is the wavelength, indicated by the Greek letter lambda, and this is defined as the distance between two peaks or two troughs. Another property that we can use to describe a wave is the number of complete waves that we get in a given time period. Usually that time period is 1 second. And so if you had one wave per second, that would be referred to as 1 hertz. Hertz and inverse seconds are interchangeable units. Now, if we consider the properties of waves and the relationships between them, we can derive some equations which will allow us to do some calculations. With wavelength and frequency, the longer the wavelength is, the less waves you're going to get into a particular time period, so wavelength and frequency are inversely proportional to one another. And with variables that are inversely proportional to each other, the product of those two variables will give you a constant value. And so the constant value that we get in this case is the speed of light, represented by the letter c. Now that speed of light constant is taken to be 3.0 times 10 to the 8th meters per second. That's in a vacuum, but again, at with the precision that we're indicating with the significant figures in that number, even if light is passing through air or water, it's not going to be all that different. So we can treat that speed of light as 3.0 times 10 to the 8th meters per second. In terms of frequency, the higher the frequency, the more waves you pack into a given time period, the higher the energy ends up being as well. So frequency and energy are directly proportional to one another, and with directly proportional variables, dividing them, taking the quotient, will produce a constant value. And so we see the constant in this case is referred to as Planck's constant, 6.626 times 10 to the negative 34th power joules seconds. And the equation that we would have there is Planck's constant equal to energy divided by frequency. And we can rearrange each of these equations to solve for whichever variable we may be interested in at a given time period. For this problem, we're given the wavelength as 2.34 times 10 to the negative 11th meters and asked to solve for the frequency. So starting with the same equation, speed of light equals frequency times the wavelength, see if you can rearrange the equation to solve for frequency and plug in the values that we have to determine that frequency. Pause the presentation at this point and resume when you have come up with an answer. Rearranging the equation to solve for frequency should give you speed of light divided by the wavelength. Substituting in your numbers would yield this setup. And solving, meters would cancel out, leaving you with inverse seconds, which is, again, hertz. And dividing your numerical values, you should come up with a final answer of 1.28 times 10 to the 19th power inverse seconds, or hertz. Please note that since speed of light is a constant, we ignore it in terms of significant figures that should be shown in our final answer. If we want to solve for the energy of a wave, we need to know its frequency. And so in this case, we're given the frequency of 3.54 times 10 to the 8th hertz. And the question is, what is the energy of that wave? So we start with the equation energy equals Planck's constant times frequency. We're solving for energy, so all we need to do is substitute in our values. Planck's constant, 6.626 times 10 to the negative 34th joules seconds. The frequency, which is given to us in the problem, 3.54 times 10 to the 8th, and the units are inverse seconds, or hertz. The seconds will cancel, leaving us with just joules. And so the final answer would come out to be 2.35 times 10 to the negative 25th joules.